Okay, so you've seen the previous two examples on optimization, so you're pretty familiar with the game plan. This example focuses on difficulty. What are we trying to do? A right circular cylinder is inscribed, let me speed this up a little bit, in a sphere of a radius s. We want to find the largest possible volume of that cylinder. Let's talk about what's going on here. Let me draw you a picture. So, we have a sphere. Yeah, and inscribed in it is a cylinder. Oh, and it has radius s. Yes. So what are we trying to maximize? We're trying to maximize the volume of the cylinder. The volume of a cylinder is the volume of the base times the height, right? The volume of the base isn't right. The volume, that's like a hybrid of circumference and volume. We need to get rid of that too, because the volume of a circle is pi r squared, and then we're going to multiply it by the height. Oh, there it goes, it's gone. So, alright, so I write that figure again. Because what are we trying to do? We're trying to get the height in terms of r, because we're trying to get one variable in our 1D maximization problems. So if you look down there, it kind of looks like you have a triangle, but the height is twice that y value, the height of that triangle. So we can go and we can get y in terms of r. So use the old Pythagorean. I need to note that s squared is fixed. It's not a variable. So just leave it s. It's abstract. And we solve, and we get y is plus or minus the square root of s squared minus r. But we only want one of those possibilities. Here we go. So y is 2 times the, or h is 2 times the square root of s squared minus r. Fabulous. So we have h in terms of r. Let's revisit our volume. So our volume of our cylinder was the base times the height. Now, mind you, that 2's not really there. So we can go ahead and get rid of it now. And then we substitute in our h. Our h was 2 times the square root of s squared minus r. I reiterate that this is just a value, not a variable. So what do I want to do with that? I want to clean it up a little bit, make it a little easier on the eye. So now that we got that guy, we can go and we can maximize the volume of that cylinder. So the volume of the cylinder was 2 pi r squared times the square root of s squared minus r squared. I should probably make those look more like r's. So we're taking the derivative. That's the derivative of the first times the second plus the derivative of the second times the first. Yeah. So we got that derivative. Oh, making them look more like r's. Let's clean that up with some fancy factoring. So that's 2 pi. Cleaning it up and writing that root with rational exponents so we can factor out those rational exponents. And you're like, what happened to the deuces? Well, I had a deuce there and a deuce there, so I had a reduce there. Now, I see we have some common factors. We have an r here, and we have an r here, and then we have a minus 1/2 there and a 1/2 there. So I'm going to go ahead and I'm going to pull out the r and the minus 1/2 because those are the smallest power of each one of those. And then we goes and we do that. So there's that r that came out. There's that s squared minus r squared to the 1/2 that came out. Then left over on the inside you have the leftovers, and that's 2 times s squared minus r to the 1 power. And then you have the r squared left over there. And we carry on, and we clean it up, and we drop that s squared minus r squared to the minus 1/2 down there to the denominator. So now that we have the proper derivative, that guy right there, what do? To maximize that, derivative, we go and we're going to set the parts equal to 0. Which parts? I'm talking about, this is in fully factored form. So this part gets equal to 0, this part gets equal to 0, and this part gets equal to 0. Because that's our critical values. We do that now. Fabulous. Let's talk a bit again about what's going on. There's that figure right there. Can you just imagine the scenario where r is equal to 0? If r is equal to 0, that means this stuff down here is equal to 0, which means what? You have a straight line. Is that going to maximize volume? No, stick. Come on, Twiggy. Now, this case over here, whoa, where s squared minus r squared is equal to 0. That means s and r are equal to 0. That means you have a disk. Is that going to maximize volume? No, flatty. So the only real case we have is this case right here. So let's go ahead and do that case now. That says r is plus and minus the square root of 2/3 s squared. But again, there's one more case we don't want. We don't want that minus case. So we got rid of it. Now since we found our r, we look in the back of the book, we take a look, and that's not it. Why? Because they were looking for the maximum volume, so we need to take that r and plug it back up into the original. And that's what we're doing right here. We're taking that r and we're putting it up into the volume of a cylinder. Alright. So then I'm going to go and I'm going to plug that in everywhere. And I do that now. Our r was that, o squared, and then that, and then o squared, and then o. We're going to go ahead and get rid of those roots with those squares. And then that's what's happening right there. And then hold up. Wait. On the outside, over here, I see that we can multiply 2 by 2 and get 4. And then in here, I see we have common terms and we can add them. Add them. And that's what's going on there. But wait, there's more. On a side note, if you're taking a look at the square root of 1 over 3, that's the square root of 1 over, or that's the square root of 3 divided by, that should be a 3. I'll fix it in a minute. So now we're plugging all that business in. And then, yeah, that's where that 2 became a 3. It wasn't really a 2. It was always a 3. Now, on the bottom we see 2 3s, which is 9. And on the top we see 2 s's and 1 s, which is going to be 3s. Yes. We've arrived at our solution. So what gets the box and the flower? You get a box and a flower. That's the maximum volume that our cylinder can have if it's inscribed in a box.